I think we should be live. I need to double check that. Yes, looks like we're live. Okay. So we are just resuming from yesterday, where we did when we did a first when we did a first introduction to Lingua Franca. So today we are just gonna move on. So the first thing we did yesterday was go through the so I mean we did a setup. Well, I talked about setting up the playground locally, and I mean it's fairly easy to do so, right? I included a link to the playground in the description of the video. It's also in the description of this stream/video. And so we went through, gosh, this thing is getting on my nerves. This here, like why is it here? Okay. All right. Gosh, everything just feels so sluggish. I don't get it. It only seems to be happening on this particular user account on my Mac Mini, where everything just feels like it's like 1 second or 2 seconds behind. It's annoying. Let me see. Alright. I made the screen zoomed in. Okay. Anyway, so we have the playground installed locally, which you can easily do. Again, there's a link for the repo for that. We looked at some of the examples briefly. I'm sure we'll get a chance to look at them more and more the more we go through the manual, reading through the manual. So today I think we'll try to get through a few of this, maybe up to reactions. So yeah, let's just jump right into it. Like that, shrink it. Okay, all right. In this section, we will undo reactors with input and outputs. Okay, input, output. The following reactor doubles its input and sends the result to the output. Okay. Notice how the input value is accessed, can talk, and how the output value is set. So this is obviously based on specifics of the runtime, where you have a context. And also one thing to note is that this is basically a global variable, at least within the reactor, because it's not passed in as an argument that we can see. Alright, this is done differently for each target language. See that for detailed documentation on this mechanism. So, okay, so setting and reading values from the inputs and outputs. So I guess generally speaking, the declared values, like they have some way of accessing and updating those values as part of the context of the runtime. And I will also assume that context is also scoped specifically to the reactor. Okay, so setting an output with a reaction will trigger downstream reactions at the same logical time. Wait a minute. I'm having this feeling that we actually I think we actually read through this yesterday. Yeah. Anyway, I guess the gist of it is so you have inputs and outputs, and you can access the values via the context. You can obviously set values, or update the value of the outputs. It doesn't really make sense to update the inputs, if I remember right. Yeah, like, oh, okay, but you can make it mutable. So normally a reaction does not modify the value of an input. An input is said to be immutable. The degree to which this is enforced varies by target language. Most of the target languages make it rather difficult to enforce. Occasionally, it's useful to modify an input. For example, the input may be a large data structure, and a reaction may wish to make a small modification and forward the result to an output. To accomplish this, the programmer should declare the input mutable. So, okay, so if the input is large enough, you don't want to, you basically want to mutate it in place, but then, okay, so I think this is analogous to the in-out binding in I guess in Swift. I think Swift has it. I think Verilog has it. I think something else has it that I know of. I think Fortran. Is it Fortran? Or I think Ada has in out. Yeah, function and procedures. In out. Well, they have in two words actually. For some reason, I think I'm used to seeing it being in a single word, but they have it in two words. That's interesting. Anyway, Swift has it. Ada has it. I think Fortran has it. Anyway, it's a way to indicate that you're passing in some arbitrary buffer. Well, it doesn't have to be arbitrary. The point is you're passing in something and you're actually expecting it back as a return value from the function with the expectation that it may be mutated or changed inside of the function or as part of the execution of the function. Yeah. So I think this will be, again, this will be a standing for the exclusive reference in Rust, the mute, yeah, that. Anyway, this is the directive to the code generator indicating the reactions that read this input may also modify the value of the input. Yep. The code generator will attempt to optimize the scheduling to avoid copying the input value, but this may not be possible, in which case it will automatically insert. It will automatically insert a copy operation, making it safe to modify the input. The target specific reference documentation, yeah. Okay. So again, and the way you handle this and depends on whatever language you have as the target. Anyway, so next, parameter declaration. A reaction class definition a reactor class, not reaction class. A reactor class definition can parameterize I don't think the D here is supposed to be there. Anyway, as follows, blah blah blah. Each parameter has a type annotation written blah 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 as one of the following forms: an identifier such as int, an array type, oh, okay. Wait, what? Why type? That's a little confusing here. Well, let's not dwell on it. The keyword time, which designates a time value. The code block delimited by that. Yeah, we've seen this before. Where the contents is any value type in the target language. Depending on the target, the type may be a generic type, which means that the type is a parameter determined at the time the reactor class is instantiated. Each parameter must have a default value, written blah blah blah, param name, expression. An expression may be a numeric constant, a string enclosed in quotation marks, a time value such as 10 milliseconds, a list of values, or target language code enclosed in the brackets. For example, see expressions for full details on what expressions are valid. For example, the double reactor in the previous page can be replaced with a more general parameterized reactor scale. Okay, yeah. So you can set the factor, which for the case of double factor will be 2. So you have the state, input, output, This is interesting though, because right now there's no default value here. So is it the assumption that the default is just 0? basically there's a declaration of variables. Well, I guess in this case, it's not even like mutable. So the fact that it doesn't have an initial value is strange. Well, yeah, it's not mutable. So yeah, the fact that it doesn't have an initial value is strange. Well, I guess one thing to remember is that this is written from obviously a reactor model standpoint and a data flow thing. Model, or I guess computing paradigm. So really, you have to think of these as being streams of values coming in. So I guess setting an initial value is probably not necessarily useful. Okay, I can live with that. But then for output, it's still strange for output though. Yeah, I don't know. Maybe it'll be specified. Well, we were just in input and output. Let's see if we can find something that says anything about default. No, nothing. Yeah, no mentions of having default values. That's interesting. I wonder why that is. I'm sure there's a solid reason why. State declaration. A reactor declares a state variable as follows. The type can be any of the same forms as a parameter. So with state, you do have an initial values. Okay, yes, that is something to keep in mind, that you have the input, you have the actual state, and then you have the output. So input and output should be really seen as being streams of values, and state or more is, obviously internal to the reactor. I do wonder, and it doesn't seem to be the case at this point, but I guess we'll find out the more we dig into this. I do wonder if there needs to be some sort of differentiation between persistent state and ephemeral state. And by ephemeral, I mean maybe state that's only available for a given epoch or a given tick of the reactor, and then it just clears out, almost like some sort of like a, what are they called, arena allocator. And in this particular case, for every like tick or cycle, because I mean, really, I think it's fair. I mean, this is definitely a state machine approach to things, and the fundamental thing with the state machine model is that you always have that next tick for, you run a tick, and doing that, things happen. And then you come back around for the next step or the next tick. And it will be interesting to be able to declare ephemeral state that's only valid for a given tick and then basically clears out for the next one. Almost like having a dedicated buffer for each request to a web server. And it's only like having an arena allocator that's only available for the duration of a request and then clears out. Well, yeah, I guess then you'll want to have a way for every request to have their own allocator. But then that allocator is probably a slice from a bigger allocator altogether, because then you basically want a way to hand out slices of the overall allocator as requests are coming in, and but also, other requests are ending, and so you have a bunch of free slices to hand out, and some that are currently taken by the currently running requests. Anyway, coming back to this, so one thing that comes to mind is, well, do we have any sort of differentiation between, persistent state of the reactor and ephemeral state for the reactor? Anyway, okay, so it sounds like Rust doesn't have it. For the Rust implementation, they don't have a concept of resetting the queue. Okay, but they do have it in Python. Good. It's actually great that they have an implementation in Python. I mean, TypeScript is great too, obviously. I wonder if you could vibe code your way into building the logic, the data logic. I mean, the data and the logic of, let's say a front-end application, then package that as a WASM component to run in a worker thread. Anyway, but yeah, TypeScript doesn't have the target, the reset thing. Well, actually, it's not just a function, it's actually a keyword. So you can qualify a state variable with reset. When this is done, if the state variable or the reactor is within a mode of a model reactor, then when the mode is entered via a reset transition, the state variable will be reset to its initial value. Okay, yeah, I guess we'll learn more about this when we come around to modal reactors. Alright, time and timers. Logical time. A key property of Lingua Franca is logical time. All events occur at an instant in logical time. So this is the tick thing that I was, the tick or epoch thing that I was just talking about in the last page. By default, the runtime system does its best to align logical time and physical time, which is some measurement of time on the execution platform. The lag is defined to be physical time minus logical time. So I guess logical time is never ahead of physical time, which I mean I think makes sense. And the goal of the runtime system is to maintain a small non-negative lag. Yeah. The lag is allowed to go negatively only if the fast target property or the fast command line. Oh, okay, never mind. The lag can actually go negative. I guess that's okay. Yeah, that would be more for simulation use cases where you probably most likely don't want to go at real time. Like you want to be able to simulate things at a much higher time density or time resolution. Like something like the Tiger Beetle simulation testing uh, harness. Yeah, anyway. The program will execute fast suppose we know we get to physical time, time values. A time value is given with units unless the value is 0, in which case the units can be omitted. Sorry. The allowable units are for nanoseconds as blah blah blah. I don't love that you can express this in multiple ways. Why not just pick one way and sticking to that? I don't love that. I think they should have just picked one for each of these and just call it a day. Like, do we really need the plural version of this? I mean, I guess it's nice to have. Anyway, the following example is just using time values for parameters and state variables. Excuse me. So 100 milliseconds, 100 milliseconds. It's funny, the space here makes me feel like this is a syntax error or anomaly. My eyes keep wanting this gap to disappear and the MS to be right next to the 100 here. Anyway, okay, so you can have time values as parameters. So you have a schedule. So this is a logical action. You can schedule an action. Okay, so start. Oh, okay. All right. So you're scheduling this 100 seconds from now. Is that what that means? Sounds like that's what it means. So at startup, you schedule an action 100 milliseconds after startup. And when that happens, when the action gets triggered, you get access to the elapsed logical time. You print. Alright. You increment the state, the interval here. Excuse me. And then you schedule again. Alright, so this is a This is a loop. This is a 100 millisecond loop. Oh, but each time you add another 100 millisecond. Okay. This has two parameters, start and increment. Each with default value, the parameter is used to initialize the into state variable, which also stores a time. The logical action A, explaining actions. Yeah, I can't wait to get to that actually, because this is interesting. Yeah, you schedule actions at a given time. I mean, it's basically like is it the set interval? No, in this case it will be the set timeout in TypeScript. Oh, I guess JavaScript. Yeah, this is basically in TypeScript. You will just do a set timeout for 10 milliseconds, and when the callback for that runs, you update whatever variable is, for the next timeout, and then you recreate the timeout. Yeah. Anyway, oof. Felt that. Anyway, is used to schedule events to occur at time start after program startup, and then at intervals that are increased each time by increment. Anchor. Is that how you will read this? Anchor, increment, anchor. Anyway, the result of executing this program will look like this. Yeah, each time you keep adding. Oof. Alright. Timers. The simplest use of logical time in Lingua Franca is to invoke a reaction periodically. So this will be the set interval functionality in TypeScript. I'm using TypeScript as an example because it's TypeScript, and virtually every language should have this functionality. This is done by first declaring a timer using the syntax timer, the name of the timer, an offset. So an offset will be from the current moment, the current logical time or physical time. And from that current time, you want to set a period, and once that period takes place, boom, you do something. Well, you can bind a reaction to that timer to do something. Anyway, the period, which is optional. Oh, it's optional. Interesting. Specify the time interval between timer events. Okay. Yeah, okay. Yeah. The offset, which is also optional, specify the logical time interval between when a program starts executing and the first timer. Okay, so it's only relevant for that first timer event. If no period is given, then the timer event occurs only once, which is basically just technically kind of like an action. An action that self-schedules almost immediately, or at least based on the offset. Uh, if no period is given, then the time occurs only once. If neither an offset nor a period is specified, then the timer event occurs at program start simultaneously with the start event. Interesting. Then why not just use the startup then? Yeah, I feel like this will be a, I don't know. I don't know that, I mean, I haven't written anything in this, so it's hard for me to judge, but I feel like it's one of those things where maybe you don't want to allow people to do this. Anyway, the period and offset are given by a number and a unit. For example, 10 milliseconds. See the expressions document, followable units. Consider the following example. I'm sorry, I don't know if I should call it ADHD or whatever. ADHD mind. Just remembered something that I hadn't thought about in a while. I think Galwa has I came up with a program or thing that I remember thinking was super cool. Since this is, I feel like I've been on the page not too long ago, and I don't remember seeing this. Yeah, since engineers can interactively select and modify UAV components such as propellers, wing rotors. Alternatively, Essence can use its bespoke machine learning algorithm to rapidly evolve UAV designs. Speedy simulation. The resulting software is DL Cookman. That can only eventuate as we can perform simulation network condition and difficult are impossible to replicate physically. To fast track testing phase, Essence incorporates advanced surrogate modeling enhanced by equipment theory and deep learning. I'm aware this is a hard detour from what we were looking at. Well, it's not that, it's related-ish. This is how rabbit holes start, by the way. You're looking at something, then your mind goes somewhere else, and guinea pig dinner. Wow, that's interesting. Oh, he's teaching as well. Okay. All right. Anyway, let's back up, back up. I'm still looking for, was it crystal? Hmm. I think it was Copilot. Was it Copilot? May have been. Yeah, stream-based language. Yeah. Okay. I'm not crazy. Because it just crossed my mind that there was such a tool from them recently. Well, that I became aware of recently. Um, I mean, this is pretty baller, by the way. It's stream based. It's a runtime verification framework, and it generates hard real-time C code. That's pretty baller. Assuming that it works as, you know, this is all true. It's pretty cool, pretty cool, pretty cool. Uh, Related project. Ogma. Is this a recent thing? Oh, it's super old. Oh no, yeah it is. Generator of runtime monitors for flight and robotics application. Noise. Noise. You know, one thing that is interesting is functional programming may actually win in the end, much to a lot of people's chagrin. Because if you think about, and I'm not saying Haskell specifically, but if you think about it, assuming that these AI models become really good and more sophisticated, and we find ways to uh, add more context, not just in terms of quantity, but also in terms of quality, and they're able to. I don't think we can expect them to be 100% right, but through guidance and repetitive reinforcement learning, they can get really better at generating implementation details and following certain um, guidelines or standards or whatever. In fact, I will argue that the more you impose on the tool, as in um, the conditions under which it can do certain things, invariants and all that, you could make well, I would say that it's not unreasonable to say that they'll actually be more effective because you're now really putting them in a box. and giving them really good direction on what it is that you want from them. And I think functional programming languages tend to have really good expressiveness. In fact, you could say to a fault. Uh, and but in the age of AI, where generating code, the cost of generating code itself, whether the code is correct or has meaning or whatever, the cost of just the tokens of code, just the symbols and all that, generating that. In a world where that becomes trivial, the ability to operate / express intent in a succinct way, but also it's not only succinct, but it's as close to exactness as possible. I don't know if that's the right way to put it. The ability to do that will actually be very valuable, right? And I think, generally speaking, I think functional programming has that over the imperative style of doing things. So functional programming may have the last laugh as these models become more and more and more sophisticated. In fact, I think I can see how they might even prefer that kind of, like, if you think about it, SQL. People hate SQL and all that, and yet it's still around, and it's, it is a bedrock. It's one of those key technologies that are very much a big part of information technology today. And the fact that it's obviously can be improved. There are many things that can be improved about it, but fundamentally, the fact that it's declarative is why it's been around for so long. You could go to the extreme and say that with some tweaks here and there, maybe SQL is the ultimate programming language 5 or 10 years from now. I don't know. Maybe that's too wild. But just the idea that you can just, you could argue, okay, natural language would be the actual ultimate. But I don't know. I don't feel that way. I don't think that natural language itself will be the thing. It may be some sort of raw input that then gets refined into some IR, just like with compilers, you do the parsing, the interpretation, and then the actual compiling. I don't know what I'm talking about, by the way. I've never written a compiler, so don't. If what I'm saying is not correct. Anyway, the point is that functional programming or just declarative programming is gonna, in the end, I think that's really where things are actually gonna land. So all the fun, all the jokes that people have made about functional programming over the years, may have to apologize for this. Oh, I'm already following him. I'm already following Netsa too. Trick base. A flight software and embedded systems framework. Damn, so space applications. I bet there was a lot to learn from the code base. Like, I guess the architecture of it all, like decisions that were made, especially around concurrency and parallelism, memory allocation, error handling, assertions and all that. I feel like there's probably a lot that one could learn from this. So it doesn't. So you can actually run it bare metal without an actual operating system. Is that what people mean when they say bare metal? I thought bare metal just means it runs on actual physical machine. I didn't know that it also implied no OS. Oh, okay. I don't know why I didn't peep that. Type 1 hypervisors. That's if I'm not mistaken, and I guess we could look this up right now, but I don't feel like it. Uh, Amazon probably has type 1 hypervisors, which then allows them to run all those virtual instances, the EC2 instances, on top of, that. Um, there's some hardcore shit right here. Programming directly on the hardware. It's crazy to think that maybe 10 years from now, this will just be the norm. If you want maximum efficiency, like it's like, oh, you're deploying your app, well, on which hardware configurations? Anyway, all right, let's. Feel like we've gone way, 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 way out of our original thing, but that's okay. That's all right. We are back. Okay, if neither on our side, no, then one time event goes. Sometimes I understand. Okay. The period and offset are given by a number and a units. I don't know that this S needs to be here. For example, 10 milliseconds. Okay, see the expressions. Documentation for allowable units. Consider the following example. You have the timer. Okay, so you have your timer. The name of the timer is T. because this is 0, it means that it's right at start time of the reactor, and it's gonna be every second. And so every second this is gonna be printing. I wonder if which one is this timer? Do I have the timer one here? No. Okay. Oof. Anyway, why am I looking at this? I wanted to see if they had the time of this example so that we can run it to actually see what it's printing. But I mean, it's pretty obvious. Every second, excuse me, every second, wait, if it's every second there's a new printing, but looking at logical time, not physical time. Okay, like it's the same. Anyway, this specifies a timer named T that will first trigger at the start of execution and then repeatedly trigger at intervals of 1 second. Notice that the time units can be left off if the value is 0 for the offset, that is. The target provides a built-in function for retrieving the logical time at which the reaction is invoked. Excuse me. On most platforms, with the exception of some embedded platforms, the return value is a 64-bit number representing the number of nanoseconds that have elapsed since. Oh, okay, then, I mean, wait, no, why is this the same? Okay, I mean, fundamentally, I get that physical is different from logical, but I'm interested to know why. I guess logic, in terms of logical time, this is startup time. So this represents this, the startup time. And the less logical time will be the next step, which is only happens if, actually, I'm not sure. Never mind. I'm not sure why this is the same every single time. Like, what increments the logical time here? Anyway, elapsed time. The times above are a bit hard to read. So for convenience, each target provides a built-in function to retrieve the elapsed time. For example, okay, logical elapsed time. Okay, well, this makes more sense. Like, these are literally the same numbers, right? Like, I'm not crazy. Oh, no, they're not. Oof. Okay, I am crazy. They're not. These are all different. Yeah, okay. These are actually all different. Okay. Alright, a full set of functions. Okay, comparing logical and physical times. The following program compares logical and physical times. Okay, so you have logical and physical. So, and we have a timer for 1 second. Okay. So logical time 0. So that's when we started. And this is physical time. And then logical time. Next one. Okay, so you have a lag. And the lag gets smaller each time. Why is that? Why is it getting smaller? Like, because the amount of work being done is the same, right? So it's not a latency thing. That is not that we can infer from everything that we've read so far. Anyway, let's move on. Hoping, well, I'm guessing that we'll come to understand why that is at some point. In this case, the lag varies from a few hundred microseconds to a small number of milliseconds. The amount of lag would depend on the execution platform. Alright, if two timers have the same offset and period, then the events are logically simultaneous. No observer will be able to see that one timer has triggered and the other has not. Okay. A reaction is always invoked at a well-defined logical time, and logical time does not advance during its execution. Oh, okay. Alright. But is that I guess, yeah, the question still is, when does logical time advance? Is it when every single reaction for the particular, I guess, step of the state machine is done? Like what actually advances the logical time? Still not clear on that. A reaction is always invoked at a well-defined logical time, and logical time does not advance during execution. Any output produced by the reaction will be logically simultaneous with the input. In other words, reactions are logically instantaneous. All reactions within the same reactor. For an exception, see logical execution time. Physical time, however, does elapse during execution of a reaction. Timeout. By default, a Lingua Franca program will terminate when there are no more events to process. Oh, really? Huh. Okay. If there is a timer with non-zero period, then there will always be more events to process. Okay, yeah. So the default execution will be unbounded. To specify a finite execution horizon, you can either specify a timeout target property or a timeout command line option. For example, the following timeout property will cause the above timer with a period of 1 second to 11 events. Oh wow. Yeah, I guess this is the part where the real time aspect comes into the fold. Basically, this is saying that whatever happens, this program right here, this Lingua Franca program, will only run for 10 seconds, come hell or high water. Right? This program is only allowed to run for exactly 10 seconds, and then it's out. Yeah, okay. Start up and shut down. Okay, so we have the platform built. Triggers to cause a reaction to be invoked at the start of execution. A special startup is triggered. A special startup trigger is provided. The startup trigger is equivalent to a timer wave outside a period. To cause a reaction to be invoked at the end of execution, so there's a special shutdown trigger, and consider the following reactor commonly used to build regression tests. Oh, okay. Start, stride, num input, state, input received, input x. So we have a streamer value x, which triggered this reaction. We print the value. If it's not equal to the count, we print to the standard error stream, buffer stream. And we exit. Well, now, are we exiting the program or are we exiting the reaction? I mean, the reaction, or are we even exiting the reactor? It's not very clear to me. I want to say that it's actually exiting the program entirely. I mean, is that safe? Especially if you're thinking about embedded and bare metal stuff. I mean, in this case, it's fine because you're not actually doing any modification before the exit. But I mean, if this loops back around after a first tick, but then it fails on the second one, wouldn't you be in a situation where you could leave due to what has taken place in the first step, to step one, that you end up in a situation where your state is not in the best condition when you exit? Well, find out. Okay, so self count, blah blah blah. Okay, stride inputs received. Okay, well, actually, it sounds like when you call it, okay, so this is actually not the Python exit. This is the exit for the Lingua Franca framework. And so I think when you invoke that, This here will be triggered. Oof. This reactor tests its inputs against expected values, which are expected to start with the value given by the start parameters and increase by stride with each successive input. It expects to receive a total of num inputs, input events. It checks for the total number of inputs received in its shutdown reaction. The shutdown trigger typically occurs at microstep 0, but may occur at a larger microstep. Oof. Microstep super dense time termination. Oh my la. Ooh la la. That's spicy. Alright, I think we're gonna stop here for today. Next time we'll jump into composing reactors, reactions, and reaction declaration. Maybe methods. We'll see. Yeah, I think that was it. We did go on a slight tangent, but I think ultimately that was a good thing. If some of you never heard of Galois before, well, now you have. Pretty cool company. At least it appears to be. Ghidra. I've never heard of this before. I want to download it. All right. Greece. Well, there's a bug here apparently. And who's gonna spot that? Chris can. Sorry. Not reading this out loud. Let's go. Now that we have found a memory layout that allows us to simulate the entry point without error, we can instrument the control flow graph with new instructions. Finally, we run the instrument control flow graph with the inferred layout recognition for collected assertions pass. Report that the party holds. Each allocation in a memory model is completely isolated from all other allocations and has a unique block identifier. Pointers into the memory model have two components: the identifier of the block, the reference, and an offset into that block. Note that both the identifier and the offset can be symbolic. Okay, so the load pointer is 0, meaning here, and no address or no offset. This sounds kind of cool. Well, not kind of. Sounds pretty cool to be able to have this mental model, formalized and actually used for runtime verification. Cross source binaries that cannot be analyzed. All right. Time to go. No, let's not get. I was gonna say let's not go down a black hole. Oh no, rabbit hole. Black hole. And yet here I am. On its face. Okay, all right. A minute this time. It's time to go. Thank you very much. If this was useful in any way, please like and subscribe, and I'll see you around. Good night.